Okay, so we are on Unit 1, Lesson 1 of Calculus, Intro to Limits. Your objectives after this lesson are to express limits symbolically using correct notation, interpret limits expressed symbolically, and estimate limits of functions. Okay, so we write a limit using this notation, and it is read as the limit as x approaches c of f of x equals L, where c is a constant or a number and L will end up being the value of your limit. Okay, approach is that little arrow, so as x approaches whatever given constant. Okay, so as you approach constant, so that should say a constant. From the right and from the left, a limit finds the value that the function intends to reach. Okay? So the limit exists only if you approach the same height from the left and the right, and it does not approach without bound. So if it's approaching without bound, that would be infinity. Okay? We'll talk more about the left and the right limits later. Okay? So you can find the limit of a function using 3 techniques. Okay, numerically. That's what we will, that's kind of the most simple way to solve your limit or find your limit. However, not everything can be solved numerically, okay? So graphically is another method. And then algebraically, and we'll talk more about algebraically next lesson. Okay, by the way, I should have said this first, but everything I'm writing down, you need to write. You don't have to highlight everything I highlight unless you want to, and you can write more than in what I'm writing. But if it's down on my paper here, it should be down on yours, okay? So, limits approaching, okay? And this is kind of the main idea of a limit, all right? So the limit of a function refers to the value that the function approaches, not necessarily the actual value, okay? And it actually will not be the value if it differs from the intended value of the line. That's the hardest part about a limit, okay? So if you look at these 3 graphs here and we try to find the limit, okay, as x approaches 1, so let's write that down. Limit as x approaches 1 of this graph, so we'll just call it f of x. What does it equal in each of these 3 drawings here? Okay? So to find that limit, you would look at where the graph is approaching. Okay, not necessarily the actual value. Okay, so let's look at each of these. If I go to 1 on x, where is the graph approaching? Okay, on the first graph, it is approaching 2. Okay, even though there's a hole in the graph right here, it's still approaching 2. So that limit would be 2. Alright, look at the next graph, okay? So if I go to f of 1, it is still approaching a y value of 2, even though the value of 1 is not 2. Okay, the line here is approaching 2. So this one is also 2, even though the actual value of this line at 1 would be this dot here, okay? A limit is different. We care about the line and the function and where it's approaching. Okay, and then the last diagram is obvious because it's closed and f of 1 is also 2. Alright, so at which value of x do all of the graphs have the same limit? 2. Alright, so that really gives you 3 examples of a limit that's still the same, okay? So these all have the same line and the same x values and the same y values, but one as a whole, its limit is still 2. One has a closed hole, or an open hole up here, but a value down below the line, its limit is still 2, okay? Because that's where the line is approaching at f of 1. And then the last one, we have a full line all the way closed, so that's pretty obvious that the value is 2 there, and the line is also approaching 2. Okay, so that is actually a graphical look at limits, so we're going to talk about finding limits numerically also and graphically, okay? So to find limits numerically, you want to make a table of x values that approach c from the left and the right, and plug them in, use substitution, okay? So we're going to find the limit numerically, and then we'll look at the graph to kind of verify that what we found is correct. Alright, next page. Okay, so find the limit numerically and graphically of the limit as x approaches 4 of x squared. Okay, so to find this numerically, we would just plug in 4 for x. We would substitute 4 for x. Okay, and that should be pretty easy to tell what that would be. 4 squared, that limit should approach 16. Okay, and let me zoom in on my graph here so you can see, and you have arrows actually if they copied off, but f of 4 is definitely at 16 even on your graph. Okay, so that's kind of just a verification that numerically and graphically we found the same value, so it's 16. Alright, so example 2, look at this one. So we have limit as x approaches 9 of x minus 9 over the square root of x minus 3. So if we plugged in 9 for x, okay, let's see what happens numerically. So we're going to get 9 minus 9 over the square root of 9 minus 3. 9 minus 9 is 0, and that will be 3 minus 3, also 0, okay? Can we divide by 0 in math? No, we cannot. So that leads to our graph over here, and you can see there's a hole in the graph, okay? So we actually could not find this numerically right now. We would have to get this answer graphically, okay? Because there's a hole in the graph from where you would have divided by 0. So this limit does still exist, but we just could not find it numerically. Alright, so as x is approaching 9, what is y approaching? Alright, 4, 5, 6. So your limit is 6. Your limit as x approaches 9 of your function is 6. Okay, and again, we couldn't do that numerically. We had to look at the graph. Alright, so example 3, if you just look really quickly, if I plug in 0 for x and sine x over x, I would be dividing by 0. So clearly, numerically isn't going to work. So we need to look at graphically. Alright, and if you look at your x of 0, right here, your y is 1. Okay, so this limit is 1. And again, we had to look at the graph because there was a hole in the graph. Okay, so we're going to use the graph to find the following. Okay, and then we will talk about limits that do not exist. So, use the graph to find the following. We should just be able to go to the x value and figure out what the y value would be. Okay, So as x approaches -1 here for number 1, here's -1 on the graph, and what is the y value? 2. So that limit is 2. Okay? Since I'm on 3, I'll just do 3 below it. F of 0. Alright, so what is the actual value of the function at the x value of 0? It is 1. Okay? That is just the value of the function. No limit there. It's kind of asking the same thing though. So it would be the same thing as if you were asked, what is the limit as x approaches 0 of this function? Same idea. Okay? Alright, so number 2 and 4, the limit as x approaches 0 of f of x, well, we just did that, 1. Okay, here's 0, my y value is 1. And then 4, the limit is x approaches 2 of f of x. Okay, that y value is 3. Alright, so if you have a graph, it's very simple to find the limits for now, okay? But limits that do not exist, those occur in your problems too. Whoops. Alright, so when limits do not exist, we write D in E. Do not exist. These limits either do not approach the same value from the left and the right, or they approach infinity. Okay, so let's look at these two examples. One of them doesn't approach the same value from the left and from the right. So if I split this graph into two parts where it changes, the left side and the right side do not approach the same value. Okay, the left side is approaching this value down here, which I think is -1, and the right side is approaching 1. So that would be a does not exist limit. Alright, and then in your second example there, the graphs are approaching -infinity and +infinity from both sides, from the left and the right. Okay, so